Hello, everybody, and welcome to the NanoVision webinar. Today, we will focus to our new product, LiteScope 2.5. It is a AFM-in-SEM solution, and I hope we will show you and convince you today that with that instrument, we will redefine the in-situ correlative analysis. My name is Jan Neumann. I'm CEO and co-founder company NanoVision, and I'm very proud and happy that colleague Peter Klapetek joined us today for the webinar, and he will share his experiences from the open hardware and open software instrumentation. In my part, I will try to introduce you the key benefits of AFM-in-SEM. I will show you the innovations and the work which has been done on LiteScope 2.5. Of course, I will show you some application examples, I hope fancy one, and some case study. Then I will pass my word to Peter.
Yes, I'm Peter Klapetek, and I will talk about open hardware digital signal processor that is inside the LiteScope 2.5.
After that, we will together summarize the webinar, and then there will be the space to answer some of your questions. You don't have to wait till the end. And actually opposite, do not hesitate to raise all your questions directly. There is a Q&A section, so directly raise your questions. There is a team of my colleagues who will answer your questions immediately. On the end, we will pick some of them and select some of them, and together with Peter, we will try to answer them. I think we can move to the slides and to the presentation. So let me briefly introduce you NanoVision. The company is located in Brno in Czech Republic, we say in the heart of the Europe, and it's a quite well known as a university city, but also mainly for the long tradition and history of the development and production of the electron microscopes. Statistics, they say that about 30% of the global production of the electron microscope is performed in Brno, and also related to development. I believe that thanks to that, we have a very strong microscopy community here in Brno, where companies like Thermo Fisher Scientific, Terskar Orsay Holding, DeLong Instruments, also NanoVision and Czech Metrology Institutes are located, but also very strong universities as a Masaryk University, Brno University of Technology, etc. I will directly jump into the main topic, which is AFM in the SEM. So what you see right now, it's a picture of the AFM LiteScope mounted on the SEM stage. And with this approach, we believe that we merge the forces of AFM and the SEM. And how this concept works, I think the best way is to show this simple video where you see by the SEM eyes, how AFM tip is scanning over the particle and actually how we are able to analyze the different properties directly inside the SEM. So if we raise the question why to put together AFM and SEM, I think the answer is quite obvious. We complement and take the best from the both techniques. AFM is extremely good in precise 3D topography with a high resolution, but also you can measure mechanical, electrical, and magnetic properties. On the other hand, we take the best from the SEM world, which is fantastic for the fast 2D imaging, broad wide field up to centimeters even, but you can also modify your surface, make the element composition analysis or crystalline structure. So taking both, putting together, this is a concept of the LiteScope and correlative microscopy. If I should highlight the three key main benefits which we see in AFM-in-SEM, one of them is in-situ sample analysis. Simply, you perform everything inside one chamber and together. The second point is correlative multimodal sample analysis, which means that we can analyze the properties using AFM, using SEM, and then correlate them together. And the third obvious advantage is precise localization of region of interest with a high resolution of SEM, where you can navigate your AFM team directly where you want. Within this approach, we believe that we provide the information and properties about the samples which are otherwise not possible to acquire or it's extremely complicated. If I show some examples how we understand, for example, in-situ characterization, so the meaning is that together with the AFM and SEM, we measured everything in one place at the same time, at the same conditions, without no need for any sample transfer or possible contamination, etc., etc. Our scientific ambassador, Mark Willinger, says, your LiteScope is like a Swiss Army knife inside your SEM. So this is what we are very happy to see. And I can show you one example. What you are looking at, it's a cathode material, cathode active material for the battery research, extremely sensitive materials. And once you imply the in-situ characterization, you can perform such an analysis on the cross-section of the conductivity. The second highlight, as I mentioned, was a correlative sample analysis. So simply, you can perform the comprehensive analysis of the properties by AFM and SEM. You can utilize our CPAN technology, which enables you to simultaneously acquire AFM and SEM data. I will talk about it also later on. And then we can show you such an example. What you see, it's a duplex steel. So by the SEM, you can visualize and analyze your surface of interest, region of interest, and then using AFM, you can measure surface topography, magnetic properties, surface potential using KPFM, and all of that you can correlate into the CPAM images. Third one, it's against most straightforward one, precise localization of region of interest. If you look on this video, when you see the AFM tip, how we point to the nanowire, there is no other way how you could measure the mechanical property of such a nanowire than using the AFM inside the SEM. I have mentioned several times the CPAM technology and correlative probe electron microscopy, as we say. So I would like to describe and explain how does it work. So this is your sample. Then we can take an AFM probe, focus the electron beam close to the AFM tip, and then we can start to scan with a sample. Electron beam and AFM tip remain static, and with a certain offset between each other is kept. But during the measurements, we can simultaneously acquire both SEM and AFM data. And then after this offset reduction, we can directly correlate both informations together. And when I mentioned that we simultaneously acquire all of the data, I can nicely show it to you on this video where you see our user interface, and we are simultaneously acquiring the different channels and data from the AFM and also the SEM. So you see topography from the AFM, you see secondary electron signals, backscattered electron signals, and you see that simultaneously we measure also the local elasticity. So this is the approach for correlative microscopy which we can offer. So together, the CPAM technology enables you to simultaneously acquire data and get really the best from both techniques, as you see on this example. As I mentioned, it's not only topography which we can offer and bring to the SEM. It's a broad variety of measurement modes and properties which we can measure. So first of all, we can measure mechanical properties like topography, surface roughness, elasticity, or hardness. We can measure several electrical properties, local conductivity or surface potential mapping. You can analyze magnetic properties or piezoelectric properties and piezoelectric domain. But also you can perform several spectroscopy analyses like IV characteristics or FZ curves. And as I mentioned, we propose fully new method, which is correlative probe and electron microscopy. So this is comprehensive analysis which we bring into your SEM. So what are the application areas? The key of them, first of them is the material science, of course, for 2D materials, batteries in these days. But we can analyze different nanostructures or quantum dots. It's very useful for semiconductor applications, R&D or failure analysis, and also it's extending application for the life sciences. So with that, I'm very thrilled and happy to introduce you our new LiteScope 2.5, which was released something like 1 month ago. And I'm happy to share the new insights about it. So the main innovation which were following our reasoning, innovating, and delivering the product, is a completely brand new control unit nanobox. We have done it together with the Czech Metrology Institute, and I truly believe that this is the next level of imaging. So if we would go in a bit of more details, and I would like to show you how to leverage the key benefits of AFM-in-SEM and supported by the new units. So we were pushing forward to even progress the in-situ correlative analysis, but putting a lot of effort into the optimizing and time-efficient workflow. We increase the performance inside your SEM, and I'm very proud to show you how we integrated open hardware design. With that, I'm convinced that this state-of-the-art of the electronic unit fulfilled the market and generally community needs, and I'm happy that all of that was designed, developed, and produced in Brno region. Because to be honest, for me, it's a part of the sustainability that products are simply developed and produced locally. Within the concept of the new nanobox, we followed bi-directional philosophy. The first part of that we were focusing and trying to make a easier life for the new users, or also for the SEM users which are not that experts in the AFM field. So we optimized the user face. We did different layouts and try to automate it as many functions as possible. But also we keep the space for the experts. So we still keep the full control above the microscope, almost without limitations. We have a different inputs, inputs, outputs to enable the connection with the another accessories, and still we have a possibilities for the scripting and realizing the experiment according to the design of the scientists. So if I will have a look into the specification of LiteScope 2.5, so from the mechanical point of view of the design, it did not change that much. So I'm happy to keep the small size, a very compact size. So it's about almost 12 centimeters. It's about 8 centimeters to the width. The weight is less than 500 grams. It can be operated in the vacuum or the ambient conditions. But what we have significantly improved, it's a noise floor. So currently we can state it's up to 35 picometers. Regarding the scanning configuration, so we keep the very large scanning area, so you can scan up to 100 micron X and Y direction, and 20 micron is in a Z direction, with very nice resolution, 0.2 by 0.2 in X and Y direction, 0.04 nanometers in Z direction. LiteScope can be still implemented in most of the major SEM manufacturers: Zeiss, Thermo Fisher, Tescan, Hitachi, and Geo. I will show you and highlight some specification from the nanobox unit. So as I mentioned, it's based, and the core is open hardware digital signal processor Redefining. Peter Kapetek will talk about it in more details, but it consists of 2 locking amplifiers which are operating up to 2 megahertz, so you can utilize almost anything, any probes which you would like to use. There are 3 20-bit AD converters, so it ensures that high resolution, full scan range, and then there are the additional possibilities to bias the tip, bias the sample, etc., etc. We have also improved the software. So it's still web-based interface, which means you can run it on the different instrumentations. You just open the web browser and put their IP address. We worked a lot on the user's accounts and the different layouts. We simplified workflows, and we made an automated function for automatic probe tuning, but also for the correlation of AFM and SEM images. I will show you more details in a minute. So if I would take the key innovations and the features which are bringing the values for you, it's definitely ultimate performance. It's your SEM, which we can reach with the LiteScope 2.5. We added the 2 new measurement modes, so more parameters or properties of your samples you can measure. We optimize the workflow, and really I'm very happy that we can introduce and pioneer the incorporation of open hardware design, which has a lot of benefits for you. When I talk about the ultimate performance, so what we mean is on the scale of 20 micrometers in the Z range, we keep the noise level up to 35 picometers. And I can demonstrate it on this nice sample. So what you look at, it's a silicon atomic terraces. And actually, we put that directly into the electron microscope and simultaneously acquire AFM and SEM data. So on these terraces, there is a well-known and established step height, 314 picometers. And you can look at how we nicely were able to visualize that and also the measure the height and also evaluate the surface roughness. I wanted to say once more, it's measured inside the SEM, and actually during this measurement, both AFM and SEM data were acquired. I would also highlight the performance of the electric properties, so which is mainly related to the techniques like conductive AFM, IV curves, or KPFM. So we have a current range, which we can measure plus minus 50 nanoamps, with the noise level about a bit of more than 2 picoamperes. You can bias the tip or the sample plus minus 10 volts with the accuracy of 0.3 millivolts. What it means that I can show you on this example again. It's a cathode active materials cross section, and because of the performance, we are able to measure and analyze the inner structure of the particle and actually see the local conductivity of the individual grains. As I mentioned, we implemented 2 new measurement modes. So one of them, it's a well-known phase imaging in the AFM community. So it's a method which enables you to measure mechanical properties such as elasticity, adhesion, or friction. And so you can correlate the topography with the mechanical properties. The way how it works is that simply you measure the topography, but also you record the changes of the phases, and phase corresponds to the mechanical properties. So this is how it's made and how we measure. The second method, which we introduce, is the electrostatic force microscopy, which actually measure the interaction forces between the tip and the sample. So what you measure is actually the surface potential due to the negative charge areas or positive charge areas, and you measure in the way that you have a conductive probe, and simply the probes feel the electrostatic forces which you can record. Altogether, we are again offering multiple tools to analyze your sample and properties inside your SEM. And also, I'm happy to say that all of that can be operated with one new control unit nanobox. One unit to rule them all, as I have learned from the Lord of the Ring. As I discussed that we have optimized workflow and simplified operation, I would like to show it on a few examples. What we have done, we have redesigned the software, we automated operations, and we also use the AI to enable advanced data processing. So when we talk about the optimized our software NanoView, we have prepared the specific layout and workflow for individual techniques. So to measure the topography and the AFM, you have one technique. If you want one layout, if you want to measure magnetic properties with the MFM, you have a different layout which is optimized. And for example, for techniques like KPFM, which is a bit of more complicated, you have another layout. What's the difference? Mainly that you see just the parameters which you need to perform your experiments properly. All the rest is just hidden somewhere behind and does not bother you during the measurements. We have also automated the AFM probe tuning. So within the few clicks, you can just automatically optimize and tune the probe. I can show you the video. So you power up, then you just press start. And on the background, there is a procedure which tune and search for the optimal condition for the probe. When it's ready, again, you are ready to approach, one click, and you start to approach with the probe to the surface. So you can use it for many different probes, many different techniques. And once you land to the surface, you just press start and you can start to measure. So it's very simple and very straightforward way within few clicks, you can start to perform your analysis. As I have mentioned, we have optimized also the way how we do with the data processing. So as any techniques, also AFM has some artifacts during the measurements, and I will show you how we implemented the AI solution to correct them. So the way how AFM is measured, that you are measuring back and forth with the AFM tip. So you get the so-called trace image. So this is a one direction. If you go to the other direction, you get a second image, which we call retrace. If you look closer, you can see that on the object, you see some artifacts, which in this case, this is a overshooting, and which can be automatically correlated via the corrected via the automated function utilizing machine learning. Normally, you do it manually with the data processing. In this way, in one click, we develop the technology which can simply mitigate these artifacts. Again, you can use it for the whole image, which is where the artifacts are mitigated. The similar approach we use for the correlation of AFM and SEM data, where we utilize our CPAM, where we simultaneously measure AFM and SEM data, but they are slightly offsetted, as I mentioned. So what we do is we take AFM and SEM data, we apply machine learning algorithms, because we have trained a neural network to recognize the fit, and within one click, you get the very nice the correlation of AFM and SEM. If you correlate it, you can get such a fantastic data as you can see here on the image. I would like to show you that it's very straightforward for the users. So on this video, you can see always on the left image, this is a one channel which we correlate or work somehow with. On the right side, it's a second image. So currently, we want to correct the artifacts. So you see the race and retrace images. If I start the video, so you see in one click, AI automatically calculate and correct the data. This is the first step. In the second step, I can just select the channels which I would like to correlate. In this case, the SEM. I try to compute, and within a while, you have a direct correlation of AFM and SEM data. And then you can have a look, you can check if the correlation fits or not. And in this case, it's fantastic, so we do not have to do anything else. So you see, during the few clicks, you are able to get rid of the artifacts and correlate the AFM and SEM data. We think also about the experts. So I just wanted to ensure you that implemented also the workflow for the people who like to play with the parameters and would like to optimize everything by themselves. So still there is a full control of the LiteScope. We have implemented active schematics, which can help you to advise and drive your experiment, and still you can utilize the scripting possibilities to customize your workflow. As I've mentioned, core of the NanoBox control unit is based on the open hardware digital signal processor Videon. What does it mean, open hardware? It means that all the data drawing and codes is available and open for everybody use. So if I should say some aspects about the integrating open hardware into the commercial product, it's very kind of straightforward, but still always Redefining can be operated autonomously. Once we deliver overall system with the LiteScope 2.5, you can make sure that all warranty and support and everything is fully controlled by the NanoVision once you keep the still standard operation. And also in this case, you have all access to the LiteScope electronics, drawings, code, etc., etc. So what we see as an open hardware concept benefit, it's a transparent, traceable, and accessible methodology, because you exactly know what is going on. You see the code and you see the drawings of the electronics. You can share your know-how within the community, because everything is open. And also it enables the expert users to further develop the new methods. And from my perspective, I see that also this approach is bridging the gap between the academia industrial development. Let me share a few applications examples with you to motivate you and inspire you what can be done with the AFM inside the SEM. So I'm very glad that recently many publications appeared using the LiteScope. So later on, you can check that within half a year there is many of them. So I choose some of them, and I would like to share the story or the applications. So you have seen several times today when I was talking about the battery research, cathode active materials. I will show it once more in more detail, because this is extremely high topic. So once you are working with the batteries and you use cathode active materials like NCM, which are dispersed in the solid electrolyte, it's again extremely sensitive, air sensitive material. So using the in-situ characterization, you can use a focus ion beam. With optimized workflow, you can prepare the nice cross sections, and then you can come with the AFM tip without any worries about the contaminations of oxidation. You can simply perform the measurements, and within the together one measurements, you can measure topography to see the level of the polished surface after the fib milling. You can nicely visualize the current map, so local conductivity on the different grains and how they are connected. And also, so always you can check the SEM sample to visualize where you are located. Another application I took from the duplex steel. I also show this part of the story. So it's a highly used materials which in these days require the complex and multimodal analysis of the mechanical, chemical, and other properties. So in this case, you can take the metal, you can polish that and visualize the individual grains using backscattered electron or other techniques. Then directly using the LiteScope, you can measure magnetic properties of the different domain grains and see the domain structure. You can identify the possible contamination, and using KPFM technique, you can identify the different surface potential and identify contaminants. And also, you can directly correlate the topography with the SEM signal using our CPAM. So this is a very nice example for the analysis of generally the metals. I would highlight another example for the 2D materials, in this case molybdenum carbide, where we have these materials is prepared by CVD deposition. It's a very famous and unique materials, and so what we provide is a tool for the complex analysis. So use SEM, so you can navigate and define the flag which you would like to analyze. Then you can measure it in the details, perform EDX analysis, for example, to get the chemical composition, but also you can perform AFM measurements to see the surface roughness, step heights, etc., etc. By the end, you can combine everything together via the CPAM technology. I picked one example which was recently published. It was cooperation with the group of Professor Preisler from Masaryk University, where they are trying to develop the methods using the laser desorption and ion mass spectroscopy to be able to individually analyze gold nanoparticles. So what they do in the mass spectroscopy, they take a laser, they illuminate the individual nanoparticles, which partially desorb and ionize, and then using the mass spectroscopy, they analyze the data. Why they needed AFM in SEM? Because for them this was crucial to understand the dynamics of the melting and changing of the individual nanoparticles. So with that, they could localize it by the SEM, and then we have provided a full range of the data about the different shapes and topography of the nanoparticles illuminated by the laser. Read the paper, very nice, and I believe important work for this field. The second recently published paper is related to the production of spider silk nanowires. So we have cooperated with the Professor Gustafsson, and as you can see, they are trying to develop the method for the biomedical application, which would use the spider silk nanowires to be able to support the growth of the different cells. So this is how it looks like, and then they needed a tool to be able to measure the dimensions, but also the mechanical properties of such a tool. So with the AFM tip, we could reach the individual nanowire, and we could start to push to the nanowire and measure directly young modulus and other properties with the AFM inside the SEM. And this was our contribution to this research. And there is many more applications which I would like to share with you. Maybe next time. There is maybe next time. So just enjoy it or contact us later. Before I will pass the word to Peter Klapetek, I would like to announce one of our activity which we have. We just founded the In-Situ Microscopy Alliance, where together with other companies and scientists, we try to connect the industry and academia together to leverage in-situ microscopic characterization solutions, tools, and services, because we really believe that these techniques has the capabilities to significantly contribute to the sustainability in the future, as you saw, batteries, semiconductor, and others. So again, the Mark Willinger was kind and cooperative with us, and he answered the question, why? Because we need to observe things while it happens. So within the In-Situ Microscopy Alliance, we are 4 founding companies. So it's a nanovision bringing AFM inside the SEM chamber, so performing in-situ analysis. There are partners for Imina. They are doing fantastic nanoprobing system so you can measure the different electrical properties. In a group, there's a company, Analyses, producing fantastic nano indenters where you can perform various of the mechanical testing inside the SEM. And the fourth partner is a Point Electronics, dealing and focusing on the signal acquisition and data processing in the electron microscopy. So together, we can convert actually any electron microscope into the in-situ microscope by adding the tools for electron microscopy signal acquisition and processing, to put their in-situ mechanical testing, to put inside the AFM, to put inside the nanoprobing. Also, additionally, you can think about the control environment inside your SEM or changing the temperature. So this is a comprehensive in-situ microscopy, and please stay tuned. Our webinar is coming soon, so we will bring you together our mission and vision about how to push this interesting field forward. So with that, I would like to pass the word to Peter Klapetek to talk about a bit more about LiteScope. Thank you very much.
Okay, thank you. Hello again. I'm Peter Klapetek from Czech Metrology Institute, and I would like to talk about the open hardware digital signal processor that is inside the LiteScope 2.5. I'm coming from Czech Metrology Institute, which is a national metrology institute of the Czech Republic. Every country has its own national metrology institute that is dealing all the units, maintenance of national standards, dissemination of units, and many other tasks. And this is the Czech one. So you might know your country's one, which could be National Physical Laboratory, PTB in Germany, and many others. And these metrology institutes cooperate on many areas, namely in the traceability, comparisons, and this type of metrology work. I'm coming from Department of Nanometrology, which I'm leading, which is at Czech Metrology Institute here in Brno. And we are focusing on development of scanning probe microscopy methods first, and Then some other methodological work and a lot of simulations, SPM data processing, and different SPM analysis. So our main mission is to make scanning probe microscopy quantitative, and we are doing this for many years already. Scanning probe microscopy can be used for many purposes, as you have already heard, and the metrology institutes like this method, especially because it is relatively easy to make it methodologically traceable when it comes to measurements of dimensions. It is a bit simpler to measure the dimensions properly with a scanning probe microscope than with a scanning electron microscope, as the things are quite rigid, and you can attach easily, for example, interferometers to get the traceability to it. But people want to measure also the other mechanical properties, electrical properties, all the other properties that you might find on surfaces, and for this, SPM is also quite useful. However, to make these measurements quantitative, it needs some extra effort, and the metrology institutes are quite active in this type of effort. The same holds for us. So we have been active on development of quantitative scanning probe microscopy methods for many years already. So we are working with all the kinds and flavors of scanning probe microscopy. Here is some example of some papers that we published on these areas. And you can see that with SPM, you can do some kind of methodology when it comes to the topography, mechanical properties, electrical properties, optical properties, thermal properties, magnetic properties, and many more. You don't see here the chemical analysis, and this is probably why you have the scanning electron microscope, as scanning electron microscopy is still much better in terms of chemical analysis than scanning probe microscopy. So all this is quite exciting work. However, what is sometimes even more exciting is building some kind of instrumentation. So the metrology institutes also quite often build a special instrumentation for example, scanning probe microscopy, because the commercial systems don't have some features that we need to get the traceability and to get the extra parameters that we would like to get. So, for example, here at CMI, we developed a metrology SPM, large area SPM that can cover measurements over centimeter ranges, or high-speed system that can do also fast and video rate SPM imaging. So when it comes to the manufacturing, developing the instrumentation, we are also doing this for quite a long time, and that's why we also were thinking since many years about building some kind of better SPM controller. So why we would like to build an SPM controller, and probably wanted to do it. So the CMI wishes were always to have something that will be universal enough to be able to be plugged in our instrumentation to perform large area SPM measurements, high-speed SPM measurements, to do the adaptive sampling, maybe to do some smarter scan paths using the compressed sensing methodology, and doing something that is beyond the raster scan that is used in nearly all the commercial instruments. Together with this, we got also the NanoVision wishes about the cost-effective, high-performance DSP that could be used in LiteScope. So we were lucky enough to get together and to get a project in a program funded by the Ministry of Industry of Trade. And in the last 4 years, we were developing this open hardware controller. So why open? Well, we like the concept of open design. The open design movement involves making the information about the products publicly shared. And this means that you can build some kind of community around the product, and the community can help you in many directions. You can get more interesting algorithms, ideas, samples, whatever. And due to this fact, it is also sometimes very successful. So you can see here some famous open hardware projects like Arduino, RepRap, or Raspberry Pi. And building something that is open is also a way how to make ourselves sure that we do things that are good enough. Because when you do something just for your lab, you don't need maybe to have all the documentation and things done that much properly. And for us, it is a nice challenge also to do something that is really well described and open for the others, so they can really use it. We have also some very good experiences with open source software, because we've since beginning we have been active in development of Gvidion open source software that is used in the SPM community for data analysis. So this was started in 2003 already, and it was originally motivated by lack of sufficiently transparent data processing software for metrology purposes. And together with David Nečas from SEITEC, we were developing this software since that, and it is now quite widely used. It supports a lot of file formats, and it can be used for nearly everything you might need when you have your SPM data and you want to process them. And therefore, it's one of the most used SPM data processing softwares in the world, I would guess. So at the moment, we are getting about 1 citation per day for this software. So we think making something open can also bring some kind of scientific outputs in terms of scientometry, which is something that we didn't expect at the beginning at all. So what is the GVScope? So GVScope is an open source digital signal processor that is designed for doing many different SPM operations, including some adaptive scanning, smart scanning in scanning probe microscope. So in fact, technically, it's a board stack that includes high bit depth AD and DA converters, field programmable gate array, and the processor. And this is all you need to run a scanning probe microscopy if you have the microscope itself and some amplifiers, preamplifiers to get the information from your probe, and piezo amplifier to control the motion. So, for example, here the microscope is the LiteScope, and the amplifiers are inside the nanobox. And then our DSP, the GVScope, does all the measurement work. So it does everything else that you need to do to run the experiment. Technically, it contains the RedPitaya FPGA board, which by chance is also an open software. It features very fast AD and DA converters and the FPGA, and to it, the custom built boards with the high bit depth AD and DA converters are stacked. So all this together is the GVScope. The main features were already mentioned a bit in the previous talk. So it's definitely the feedback loop for the SPM operation, including the standard probes using the optical pickup, or the self-sensing probes like Akiyama probes that are using the FM detection via phase lock loop. It has the 20-bit DA converters for running the scanners, which is especially important in the Z direction, because in Z direction you usually need to have really very high resolution. It has 16 simultaneously sampled 18-bit inputs, 16-bit outputs. It has 2 lock-in amplifiers, plenty of other stuff like serial interface, and it also has a variety of ways how to perform non-raster and adaptive and smart measurements using different technologies. So we have tested a lot of different scanning probe microscopy regimes, as was already mentioned, like AFM, conductive AFM, magnetic force microscopy, KPFM, scanning tunneling microscopy, and these techniques with it. And also inside it uses a lot of concepts coming from the Gvidion open source software, like saving Gvidion XYZ files, general clouds of point data, using the GVScan library for adaptive scan path generation, and also using GVFile library that was produced by David Nečas for passing the objects and storing the objects in different levels of the architecture. So what you get with it, what does it mean that it's open source? You get all the files. So you get the hardware source files, like all the electronic circuits and the layouts. You get the software source files. So on the RedPitaya board, there is a server running doing all the work, which also uses a library that is used to run the stuff on the FPGA. So you get all the source files, which are mostly C files, and Xilinx Vivado project written in Verilog language for the FPGA side. And you get all the documentation. So the first thing that you can do with it is to just have a look on it. This is quite important. This was even the idea behind development of Videon, because sometimes you probably do not need to hack something, but you want to understand it. So this is the first thing you can do, and you can have a look on it, and you can better understand what does the microscope do, which sometimes is quite useful, not only for the methodology purposes. So you can check it on the web pages of the project. So there is much more technical information, which I didn't mention here. And you can also here see some of the images obtained using the standard optical level technique on the top, then the magnetic force microscopy image at the middle, and then I think this is some measurement with the self-sensing probe on the atomic steps as well. So there are many things that were already measured using it, and we are using it heavily also for the other instrumentation that we have at CMI. To show the performance, it is always a little bit hard to show performance of some SPM system, because it's not only the digital signal processor, but it's all the chain starting with the probe, then the DSP, the amplifiers, the mechanics, the environmental enclosure, and all these things. So we wanted to show this on the real world example. So these are the silicon steps, monoatomic silicon steps that were produced by PTB in Germany by Ludger Kenders about 20 years ago. So you can see that sample is a bit dusty already. However, this type of sample is a new traceability route for nanometrology, as it is the novel potential secondary realization of meter. So it has a special features for us metrologists, so we really like this type of samples. And here you can see the A and C are measurements using the LiteScope DSP, B and D are measured using a commercial SPM, quite good commercial SPM, and you can see that the images are quite similar, and also if you would analyze it, the noise levels are quite fine for the LiteScope. So we believe it's quite good electronics. And what is also interesting here, when we are using LiteScope, we didn't need to artificially reduce the Z-scanner range, which is sometimes done in commercial microscope, to increase the resolution, because here with the 20-bit DA converters, we can simply use it as it is, and we get the resolution. When you want to go beyond the boring rectangular equally spaced images, you can use scripting. So that's another feature of LiteScope. You can do scripting, and for this the Lua language is used. So this is a quite efficient and lightweight scripting language that was quite easy to embed inside the server. And you have a lot of different commands you can use, and I think especially Nanovision uses for nearly everything the Lua scripting. So they are our first user in terms of testing this, and we are happy for that. So you can run nearly everything as a script, and you can also use some additional statistical functions that are here that can already at the DSP level during the scan do some data pre-processing and make some decisions. So an example of this is shown here, smart scanning using the Lua scripts. So here you can see two examples. The top one is quite simple. It is a grating that is slightly rotated. Using a simple Lua script, you detect the angle of the rotation, and then the rest of the scan is done in the appropriate direction. So your profiles are really perpendicular to the grooves of the grating. The bottom example is a bit more complicated. So this is measurement of a rough surface, where a script that is shown here calculates after each line the local correlation length, and makes a new profile at the position where the lines do not correlate. So when you are interested in the statistical properties of the surface, you can use this to save a lot of time measuring only the profiles that are not correlated. So getting really data that are independent and can provide a maximum of statistical information. When it comes to the adaptive scanning, we also use it for the other systems that I mentioned that we have at CMI. So here you can see a large scale example measuring an optical lens. So when you are working with the optical surfaces, sometimes you would like probably to map both the roughness and form of surfaces. And here we did a millimeter or over centimeter scan on the optical lens. And using the Lua script, you can easily, again, write a simple script that finds the top position of the lens and then performs some kind of smart motion across it and produces data that are measured much faster than if you would really do a raster scan over all the lens. You don't need to do anything very special to process the data because Gwydion open source software can already handle the XYZ data, the general clouds of data. So when you measure something over some very complicated scan path, you simply load the data into Gwydion and you process the data. So you don't need to do anything special. And this is also a benefit of Gwydion, that it really produces the data that can be directly processed in Gwydion, even if the data are a bit more complicated than the traditional raster scans. The last example, use of Gwydion with something else than LiteScope microscope. So this is a use of it with the CMI high-speed large area SPM. So we are using the large area scanning stage using RB rings that is combined with a high-speed stage that we got with our cooperation with Bristol University. Everything here is controlled by interferometers because it's a metrology system. We have a range of 5 by 5 centimeters, and together with this, we had the high-speed stage with another interferometer. And using all of this, we can scan over micrometers. So the range of this image is 300 by 300 micrometers, not meters as shown here. That would be another dream. So it's 300 by 300 micrometers. And again, here we use the Gwydion controller connected to some other boards to control the interferometers and to drive the voice coils. However, still the main concept, the data storage was the same. We got a few gigabytes of data measuring all this large area, even after some averaging reduction of the data. And again, as Gwydion works with XYZ data, we simply can load this kind of data into Gwydion and then to process them. So to summarize, Gwydion is an open hardware that is combining an FPGA board with additional AD and DA converters, custom-built libraries, and FPGA code. A part of regular SPM tasks, it can be used for some adaptive scanning, smart scanning, using either the Gwydion library or using the Lua functions, that's the scripting interface. It can also be used as a demonstrator how you can benefit of using the general XYZ data in SPM, not just storing the metrics of data points, but really storing all the positions of all the points, and then probably also some time-stable information about the drift and all these additional things that make the metrology life much easier, and we hope that make also your life much easier when you are doing the SPM. We have also many development plans. We are continuously working on it. At the moment, we are continuing the development, especially within the Ampere project, METEX SPM, that is about the high-speed microscopy. So we never stop with this. And with this, I would like to thank you for your attention.
Thank you very much, Peter, to sharing your experiences with the open hardware. I would like to maybe highlight once more that for those who are not that familiar with the AFM community, so Peter and the group in Czech Metrology Institute is really well known in the AFM community for their job. So we very much appreciate the long-term cooperation. With that, we are coming to the conclusion part. I would like to, show you and encourage you to reach us. So Nanovision as a company, we have a broad range of the partners covering almost all the globe. So don't be shy, contact us directly or contact our partners. I would like to encourage you also to visit our webpage, follow us on the social media and on the YouTube account, because we try to regularly share there a lot of content and a lot of application examples, product materials. So currently, all webinars for also this webinar will be uploaded to the YouTube, and you can watch them later on. So for you who are looking at this webinar, you can also check the previous webinar and search for the topics which you like, or contact us directly. I would recommend to contact Tomáš Kostovčík or Veronika Hegerová. You can meet us on many conferences. So the key one, which I will say, it's M&M or Euromat this year or later on in Busan in South Korea. So we are looking forward to meet you in person there. And let me make a brief summary of the webinar. So on the beginning, we try to encourage you and show you the key benefits of AFM-in-SEM. As we see, in-situ characterization, correlative multimodal microscopy, precise localization of the region of interest. We try to introduce you key innovations and benefits of LiteScope 2.5, new generation of the LiteScope, where we showed, I believe, ultimate performance, which we can achieve inside your SEM. We showed you additional measurement modes. We show you optimized and I would say really easy to operate workflow. And we showed you how the open hardware can be integrated into the commercial product. I tried to present you several application examples, but you can search much more again on the another media. And thanks for Peter Klapetek to share us the details about the GWISCO, but also about the open hardware and open software philosophy, because I believe this is an important part of the community that we should share the know-how about the hardware to push all the fields forward. With that, thank you very much. We are getting into the last part, which is a Q&A. So with the colleagues, our colleagues have got several questions, picked the several questions, and we will try to answer them with Peter live. So I would take the first one. So the question was, does it need different kinds of the tips for different properties measurements? Yes. So if you want to measure different techniques and different properties, you select the different AFM probes. They might be magnetic or conductive or just the pure silicon. So depending on the methodology and properties you would like to measure, you take the correct tips. We always guide with advice which one are the best. So for each technique which we show and use, we have a dedicated AFM tips which you can use. Maybe I will.
Yeah. This is probably on you. A question if the LiteScope is suitable for all brands of SEM. So yeah, it was mentioned already, I believe, and
yeah. So I will try to answer. The LiteScope, you can install almost any SEM for any brands, definitely. Only limitation which might be for you to install LiteScope into your SEM is the size of the chamber. So if we will physically not fit into the chamber because it's too small, then it's not compatible. Otherwise, we have a special adapters for each manufacturer, and there is no problem, and it's very simple integration to the most of the AFM SEMs.
Then the next question is about the scanning area. So the LiteScope has 100 by 100 micrometers, as far as I know. However, theoretically, you could have another scanner running with the GWISCope at least. So I think this is technically it is not limited to any kind of scanning range.
Related to the GWISCope, it's open.
Yeah.
So depending what you connect. For the LiteScope, AFM for the SEM, so in open, it's a 100 by 100 micrometers. If you measure in the closed loop, it's 80 by 80. So I had another question, I guess, also for me. What is a typical distance between the focus electron beam and the tip during the CP measurement, during the correlative probe and electron microscopy? So the distance is as small as possible. We have reached like 50 minimum was 50 nanometers, because if you go closer with the E-beam, the A or AFM did start to shadow the electrons and you lose the scale. But normally we recommend to set the distance like 10% of your overall image. So usually few hundreds of nanometers. That's reasonable, but if you want to go to the limit, we have tested on the 50 nanometer with the 50 nanometer distance with the AFM tip and electron beam spot, and it was still quite okay.
Next question is on liquid samples. So I assume this is about measurements in liquids. So in principle, SPM can work in liquids. It depends again on probes, as mentioned. So the self-sensing probes can be also used in liquids, and I think there are some trials for that. It's not always compatible to SEM, I guess. But technically, all the driving signals and everything that you pick up from the forces might be quite similar. There are some challenges with liquids, but it should be possible if the configuration of experiments allows it.
Exactly. Maybe I just comment in the AFM field, it's a very rapidly growing area, right? To measure the life science applications, the cells inside the liquids. So also it is possible with the LiteScope. And actually, it's one of the direction where we go in environmental SEM applications. So here I have a question for the NanoView. So if I understand correctly, you don't need to sweep manually at all anymore. Yes, for most of the AFM probes, you don't need to sweep anymore. You just press one button and it automatically sweeps. Nevertheless, you still can access all the properties and do it manually if you are not satisfied with the result coming out from the automatic sweeping, or if some special probes or some error might appear, that's live. So still you can do it manually by yourself. But for the normal operation, no, just one click and it's automatically swept and aligned. So
that's all.
That's all. So once more, thank you very much for attention. Thank you for questions. I hope it was inspiring and interesting webinar for you. Reach us, stay with us, and we are looking forward to hear from your side soon. I would like to once more thank you, Peter, that he was willing to attend the webinar with us and share his experience within this webinar. Thank you very much. Have a nice day.
Bye.
Bye.